Okay, great. Thanks.
All right. All right, yeah, so I've been doing programming languages research for about 10 years, primarily in static analysis, although I've on occasion accidentally done research in parsing. And I could talk about that perhaps at some future event or later tonight if you catch me. I've also done a little bit of research into functional data structures, so I just published a paper on functional delete in red-black trees, which, believe it or not, was not something we knew how to do very well. I have a lot of wide interest in functional languages, and if you have interests outside of static analysis, I'd be happy to chat with you about that stuff as well afterward. But what I want to talk about tonight is just sort of give you an overview of what static analysis is all about, with a particular focus coming from functional languages. So we won't actually build a static analyzer for a functional language tonight, but we will use a functional language to build a static analyzer. And I think there's some inherent advantages in using functional programming languages to do that. Most of my research actually does involve static analysis for functional languages. And again, I can show you some more of that as well after the talk, but it's a little bit more complicated than doing static analysis for imperative languages. With that, there's really only one major idea that I want to get across tonight, and that is a basic technique for how to build a static analyzer. And this is something that we've really been, this general technique is something we've been pushing in my lab now for the past, 4 or 5 years. And the idea is to take an interpreter and written in a purely functional style. So you basically write an interpreter for your programming language. You do it in a purely functional way, so no side effects. So what you really have at this point is actually a mathematical artifact called semantics. And then we have some transformations you can do on that to turn it into an abstract interpreter. An abstract interpreter also has a specific meaning in the context of programming analysis. But what it really means is that it's a static analyzer at that point. So you start with an interpreter, you do some transformations, and it becomes a static analyzer that can tell you things about your program. And so tonight, we'll actually do some live coding, and I'll show you this technique, which I will claim is very powerful. We actually call it abstracting abstract machines. And while I will only demonstrate it on a very tiny language, I promise that it will scale all the way up to real ones. This simple technique, which I'll show you tonight, we've scaled it from everything from the Lambda calculus to full-on Racket to Android and beyond. So it's going to look simple, but I promise it will take you as far as you want to go in terms of analyzing programming languages. All right. So what is static analysis? Well, rather than starting off with sort of a definition of what static analysis is, I think we can end up at what static analysis is by asking the question, why do we want static analysis? And to motivate that, I'll just go over what I hope some truths that we can take to be self-evident, but particularly amongst a group of developers. And then from there, try to solve for why we need static analysis. So I assert that software is too slow. You can disagree if you want. Hopefully none of you will. That software is too buggy, and that software is certainly too insecure. So why is it that software is all three of these things? Why is it too slow, too buggy, and too insecure? Well, I would say that software is so poorly constructed these days because we can't engineer software. Which is interesting because we do have a field called software engineering, which I assert is more or less fraud. Because if you compare it to other kinds of engineering, it's not quite the same thing. And I think this cartoon from Calvin and Hobbes, which I saw this as a kid, and I remember when I was learning software engineering in college, like this cartoon like flashed into my head, and I went out and found it because I feel this perfectly describes the way we build software today. And what's going on here is they're like driving over a bridge. Of course, Calvin asks his dad, "How do they know the load limit on the bridge?" And his dad, of course, replies, "Well, they just drive bigger and bigger trucks across the bridge until it breaks, and then they know the load limit." And of course, then you rebuild the bridge. And it's funny because we know that's not how we build bridges. When you build a bridge, if you're a civil engineer, you have statics and dynamics, you have Newtonian mechanics, you have all sorts of predictive models that will tell you how a bridge is going to behave under load. But if you're building software, this is what you do. You just build lots of test cases and you cram it through and try to get your software to break. So this is the state of software engineering in 2014. That's best practices. So I argue that, in the same sense that other disciplines in engineering have predictive models that they can use to engineer, we don't have those in software. We can't engineer in the way that they can. That's because we can't predict the behavior of software. So why is it that we can't predict the behavior of software? What's different between a computer program and a bridge? Exactly. A bridge is not Turing complete. I certainly hope not anyway. So we can't predict software because Alan Turing said you can't do it. And that's all there is to it. He just said you can't. You cannot predict when a program's going to halt. He gave us the 11th commandment, which is that you cannot write an algorithm, which in general will take a program and its input and tell you whether or not it halts all the time. So, whereas other disciplines like physics have things like black holes, which lead to event horizons beyond which we cannot see, computer science has what I like to call loopholes. Because loops are sort of the fundamental construct, and things that create loops are the construct of computer science that create our event horizons. The points beyond which we as programmers cannot reason, at least with any reliability. So, what this means for all practical purposes is that if you have an interesting question about the behavior of a program that you want answered, it's going to be undecidable, because it's going to be in some way, or you're going to be able to reduce the halting problem to that question almost certainly. Unfortunately, even though we can't have software engineering, we need software engineering. Because we would like to be able to predict software or the behavior software so that we can do things like guarantee the absence of crashes, or find ways to parallelize our code, or look for security vulnerabilities, either incidental or deliberately inserted. So we do need software engineering. And the good news is that there is a loophole in the loophole, and that this is really what static analysis is all about. So what the halting problem says is that you can't always say yes or no. So as long as you insist that you always have to have an answer, then you can't do it. But if you're willing to say maybe or I don't know, well, now becomes a very solvable problem. The simplest static analysis, or the simplest analysis for termination, would just say I don't know all the time, and that's fine. So as soon as we allow the possibility of saying I don't know, we can actually start to do reasonable reasoning about programs. And that's what static analysis really is. It is reasoning about programs or their behavior without running them and without running through the halting problem. So we get as close as we can as possible to solving the halting problem without actually solving it. That's what we want to do. And so the way I like to you visualize what we're doing in static analysis is imagine the execution of your program as a path through some state space. So imagine every dot is a state of execution. You're just leaping from one to the next. There are regions in this state space where you want to prove your program doesn't go. You want to prove, for instance, that you avoid regions where you overflow integers, and you avoid regions where you dereference null pointers, and you avoid regions where you overflow buffers. You'd like to prove that the actual execution of your program doesn't go through those regions of the state space. So what we do in static analysis is we basically construct upper and lower bounds on this state space so that we don't know the exact line of execution, if you will, but we can get an approximate region of execution for the program, and we know that the actual execution is somewhere in that blue region right there. And if we have a bound like this blue region, then it's tight enough to say, well, this program, whatever else it may do, it certainly won't go into here, which means it certainly won't overflow an integer, and it won't dereference a null pointer. But even though it doesn't overflow a buffer, the bound isn't tight enough to show that. So what a lot of research in static analysis looks like is coming up with ever tighter bounds on that line to get us closer and closer to the answer without actually getting there, which would mean we've solved the halting problem. So that's sort of the quick summary, high-level summary of what static analysis actually is. And so what I want to do now is actually do some live coding. So if you've turned your brain off, you have about 30 seconds to turn it back on, because I will ask you questions. And so what we'll do is just build up a very simple sign analysis for an expression language, and then move on to building up a static analysis for a register transfer language, essentially. And the principles we use for the register transfer language will actually scale all the way up to whatever language you might want to use. So let's look at sign analysis first. So this is actually sort of like, if you look at like the theory of abstract interpretation, this is like the very first thing you'll encounter, which is, suppose you want to compute the sign of some arithmetic expression without actually computing the arithmetic expression. And what I really mean here is I want to compute the sign of it, or I want to approximate the sign. So I might get lucky and get the actual sign, but I'm willing to tolerate some imprecision. So I might be willing to what you could say during sign analysis is that it's negative or positive, but certainly not zero or something like that. So the core idea behind sign analysis is the core idea behind a lot of the core idea behind a lot of static analyses, which is abstraction. And what that means is that we're going to start operating on abstractions of values instead of the values themselves. So if we start with the integers, we can abstract each integer to its sign. So all the negatives go to negative, 0 goes to 0, and the positives go to positive. And then what we do is we come up with the corresponding abstractions for operations on these abstractions. So for instance, if we have negative 3 times 2, that becomes negative times positive, which of course yields negative. So we can say, what we can do is abstract negative 3 and 2 into negative and positive, and then come up with an answer without actually computing negative 3 times 2 to know that the answer was negative 6. All right, so let's go ahead and just build basic sign analysis. Let's just do it. And I'll go ahead and use Racket. So Racket is one of the homegrown languages at the University of Utah. It's built by Matthew Flatt. I don't know if you've had Matthew out yet or not. I'm fond of it because I think for doing programming languages research, it makes things very easy. It's got very powerful pattern matching constructs, and I do feel that it is growing in popularity. So Racket is it's like a Lisp or a scheme if you haven't seen it before. So first we need a language. So this is our language right here, and we're going to reuse what we build here when we scale up to a register transfer language. So the core language here just has integers, multiplication, equality, and addition. And of course, we're going to encode it as S expression so that we can actually deal with it inside of Racket. And what we want to do is build a function called simple eval, which will take an expression, or an abstract syntax tree for those expressions, and compute the integer. Then what we're going to do is come up with an abstraction on integers. Well, we'll use the sign one I just showed you earlier. And then we're going to convert this very simple evaluator into an abstract evaluator for arithmetic, which will give us the sign or possible signs of some expression. All right. So the process here will be start with a simple evaluator, go to an abstract evaluator, which gives us back an abstract integer, and then we'll take it from there. So let's go ahead and switch to Racket. And actually, let's cancel. I'll turn the Wi-Fi off so it doesn't bug me. Let's see. Ooh, that's tight. So all right, we all see that now? We'll see. All right. So first, let's copy over just, we don't have types, so in lieu of types, what we'll do is just copy this over and make ourselves a grammar. Oh, it's, yeah, that's, that's an image. Let's copy just the text there. Yeah, Racket is incredibly permissive in what it will accept for a character. So it's often used for instructional purposes, and so like the first week, instead of using like numbers, they'll use pictures of stuff, which you can just paste right into the prompt. All right, so let's go ahead and S-expressify this. So this will be our data type, so to speak. Somebody familiar with S expressions? Anybody not? It's like XML except it doesn't suck. Yeah, it's got its own problems, yeah. All right. And we want to define a function, simple eval, which will take an expression. And we're going to do what you always do in function programming, which is just pattern match. So one of the reasons I do most of my programming in Racket these days is actually that I think it has the most powerful pattern matching construct of any programming language I've ever used. And if I look at sort of the evolution of languages I've used over time, I've just gravitated towards increasingly powerful pattern matching. I started off, I used Scheme originally when I started functional programming. Then I found standard ML, which was the first time I really encountered real pattern matching, and I was kind of blown away by it. And then I moved to Haskell after that, because it had even better pattern matching, then to Scala, and now to Racket. And Racket actually will be the language I use forever, because you can't get better than Racket's pattern matching system, because you can write macros for the pattern matching system which are Turing complete. So if you're not satisfied with the existing power of the pattern matching system, you can arbitrarily extend it. So Racket should be good forever. And actually, I have on occasion had reason for doing exactly that. So we're going to match on an expression, and there's 4 cases here. So what's the simplest case that we can encounter when we're trying to evaluate an expression into an integer? Yeah, we can get an integer. So let's check for that. Let's get an integer, and an integer will just return the integer itself. Okay, so that was easy. What else could we see?
Simple.
So we could see one of these 3 things up here now. So pick one. Yeah, okay, we'll do multiplication first. So let's suppose we see multiplication, which has 2 sub-expressions. So this is the Racket pattern matching syntax, and what I'm really doing here is deconstructing a list literal. So I'm saying, if the list's first element is star, and its second element is anything, and its third element is also anything, then go ahead and match. And while you're at it, bind the second thing to exp1 and bind the third thing to exp2. That's what this notation right here means. So, suppose we're evaluating multiplication. What should we do? We're multiplying exp1 by exp2. Multiplying, right. So is this what we want to do? No. What do we want to do first? Exactly. So we'll do that. So there we go. So that should work for multiplication. All right, and then we'll just copy and paste for equality. Actually, well, this is going to return a Boolean, and that's going to be outside the scope of our language. So let's go ahead and actually compare them. We'll use this C-style convention for true and false. So we'll say, if they are equal to each other, we'll return 1, otherwise we'll return 0. And we could return true and false here, but I want to just keep this very simple and very arithmetic for now. And then the last case is plus. And it looks exactly the same as times. All right, so let's just test it to make sure it actually works. So we can give it something like plus 10 times negative 3, 2. And we get 4. What's that? The arithmetic is correct. Okay, so far so good. What we want to do next is define an abstraction on integers. And then basically copy and paste that code and turn it into an abstract evaluator. So what we're going to do is define an abstraction function. And if you look at the literature on static analysis, we typically denote this with the Greek character alpha. And there's a corresponding one called a concretization function, which goes the other way. Of course, it'll go into a set of integers if you go the other way. We don't always code that one up. This one we sometimes do, at least for very simple value domains. So what this is going to do is going to take us from an integer and give us back an abstract integer. And if we're doing sign analysis, an abstract integer is going to be a set of signs. And so then what we're going to have to do is redefine arithmetic for sets of signs. But first, let's code this thing up, because it'll actually be somewhat useful when we're coding. So go ahead and comment that out. There's another reason I like Racket. You can type in the LaTeX version of a symbol, and then you do Control/, and it turns it into the Unicode. So it makes it very easy to program in Unicode if you're inside of Racket, if you also know LaTeX. In fact, if you type in like the first few characters, that's all it takes. It'll match on the closest one. So alpha will take in an int, and we'll go ahead and put a signature on it. It's going to go to abstract integer, and let's go ahead and define abstract integer 2. It's just going to be a set of signs. And we'll even define sign. Sign is going to be symbol negative, 0, or positive. I also like working in Racket because I don't feel constrained by a type system. Although I do plenty of type programming too. So we'll go ahead and check. So if the integer is less than 0, what should we return? So exactly, we want to return the set that contains negative. And if it's exactly equal to 0, we'll return set 0. And if our integer is greater than 0, we're going to return, set plus. We got it. So we can just check to make sure this is working. So I'm just driving right across that bridge, you see. So far so good. Now what we're going to do is copy and paste the simple eval and turn it into the abstraction of simple eval over these abstract integers. So let's do this. We're going to change its name so it has a caret at the end. It's in math it's pronounced hat, so this is hat simple eval now. And that just means that we're now abstract. We're going to operate on abstract values. So if we see an integer for an expression, what should we return for the abstract integer? Exactly, alpha of that integer. So we'll just apply our abstraction function. Now, suppose we see multiplication. What do we want to do here? Yeah, we definitely want to simply eval hat the sub-expressions. We definitely want to do this. But can we use ordinary multiplication anymore? No. This should crash. And it's not JavaScript, so it will. Yeah. Yeah. So, and we're just basically going to, everywhere we have a simple eval, we're going to turn it into a simple eval hat. And then we'll come back and figure out what to actually do with these things. And I'm going to go ahead and cheat on equality here. So we could come up with and this will actually be homework if you want to, have a little exercise later. Instead of actually trying to figure out what the most precise possible answer is for equality, I'm going to give basically a default answer. So there's only two answers that can come out of concrete equality, and they're 1 and 0. So what's a reasonable abstract integer to just drop right here that will always hold?
0.
Exactly, 0 or a plus. 0 and plus, there we go. So that one's done. But now what we have to do is come up with abstract versions of times and plus. So let's go ahead and put hats on times and plus, and then define these things. So we'll define abstract times first. So it'll take in two abstract integers. And for now, we'll just have it return. Actually, let's define the worst possible abstraction first, and then come back and fix these things up. So the worst, what's the worst possible abstraction for multiplication?
All the signs.
Yeah, just give back everything. -0 or positive. So total loss of information, and we'll do the same thing for the moment with plus. -0 or positive. So this will at least get our code compiling, and at least it's correct again. So we can actually, let's drive another truck across. We'll do abstract addition of plus and plus. So ideally we'd get back just plus here, but because we didn't do anything intelligent at all inside of abstract plus, it just gives us back the worst possible answer, which is okay. It's correct. This is the I don't know analysis. This is the sort of the worst case, but we can do better. So what we want to do is basically compute the pairwise sign of everything in A and everything of the pairwise abstract multiplication of everything in A and everything in B. Because A is a set, B is a set. We want to check every possible combination of these two things, and then union them all together. That's what we want to do. So let's go ahead and define a helper function that works just on one sign at a time first for A and for B, and then we'll use that inside of this one. So let's see, what should we call this one? It's going to work on one at a time. Yeah, let's just call it /sign. So it'll take A and B. And the contract on this one is that it's going to take an abstract integer and an abstract integer and give us, it's going to take signs. A sign and a sign and give us back an abstract integer. All right. So we'll use the match construct again and just check to see which possible pairings we can get and give the most precise possible answer in each case. So we'll use match star, in fact. We're going to match on A and B. Oh, and I guess I should mention, if you haven't programmed in Racket before, there's no difference between curly braces, brackets, and parens. They're all the same. It's you would use one over the other for purely cosmetic purposes. They have no actual semantic value. So I could just as easily do, this. That's in case you're wondering if there's some reason why I'm using curly braces here. There's not. It's just a stylistic thing. Oops. All right.
As long as brace matches to brace.
Yeah, as long as that will get you in trouble if you don't match like to like.
But in Dr. Racket, the type of close parenthesis, it will close regardless of
right.
the type of parenthesis you close. It types to close it. It will match properly.
Exactly.
So
it will.
Open square that's your last thing, and you type a close curly, it'll put in the close square for you.
Exactly. All right. So let's see if we have plus and plus. What abstract integer is this going to become under multiplication? Yeah, just going to stay plus. So we'll do a set of just plus. And suppose we have plus and 0. What will that become? Yeah, 0 times anything is 0. So that's... yeah, we could do that, and we'll do that in a sec. And then if we have positive times a negative, yeah, negative. And if we have 0 times anything whatsoever, so that's now an underscore pattern, so that'll match whatever we have for B. This should just be set 0, because 0 times anything is just 0. Then we'll do the negatives. So if we have negative times positive, we get back negative. So we're just mirroring the above now. And if we have negative times 0, just 0. And if we have negative times negative, then this will be positive. Okay. So with access to this helper function right here, it'll be much easier to actually write the next one down below, which operates on sets. So let's go ahead and we'll use the for construct in Racket. So for star means iterate over all pairs of what I'm about to give you. And we're going to go ahead and say turn them into a list afterward. So the for construct in Racket, there's several variants of it, and this one is kind of like it's for in Racket basically ties together map and fold all into one construct. It's quite powerful. First thing we're going to iterate over is all the signs in A, and then all the signs in B. And what we're going to do is just, perform the abstract multiplication on these things. So, just to change this to S1 and S2. S1 and S2, and if we actually run this thing, then at the moment what it'll give us back is a list of abstract integers. And we then need to actually union them together. So let's actually invoke it so we can see what it gives us back. So if we do negative and positive times 0, we should get back 2 sets from this. It should be 0, 0. And we get back 0, 0. So what we want to do to go all the way to an abstract integer at this point is union these together. So let's go ahead and actually just specify what this is supposed to be. So this is supposed to be an abstract integer to an abstract integer. So to do that, actually we'll leave this here. Does anybody know in Lisps in general the way we would do something like this? What's that? Yeah, I guess we could use a reduce here. So we could use a fold here. Yeah, and apply. That's what we want to do. So we're going to just say apply set union to the arguments contained in this list. And that works. So now we have abstract multiplication. And so I think we'll go ahead and skip over defining a more precise version of abstract addition for now, just like we're skipping over a more precise version of abstract equality. But you get the idea here, is that you can start off by producing an abstract interpreter that's that always says I don't know, and then start refining it from there by exploiting structure in the abstractions you've created. All right, so let's actually run the abstract evaluator. Let's just do simple, actually, right here. Simple eval hat, do times 6 negative 2. Sorry, I think this is I think it was negative 3 2. I think this is the example from the start, and it'll tell us that whatever it is, we don't know what it is, we know that the result is negative. That's what the very simple analyzer has told us in this case. All right, so comment these out. Keep going. So any questions so far on the sort of the general methodology or what we're doing here? Because all we're going to do is just scale this up. This idea of take an interpreter, convert it into a static analyzer, all the while remaining purely functional. So done with this. So now we've done signs, let's go ahead and do Turing machines. It turns out Turing machines are relatively easy to do, and it sort of gives us the key idea behind static analysis in general. So with a Turing machine, you have a set of control states. You have, I assume everybody in a group like this is aware that Turing machines are a universal model for computation. So if we can do it to Turing machines, you can do it to anything. A Turing machine has a set of control states. It has a set of transitions between control states. It has a marker for whatever the current state happens to be. So this is the active state. And of course we have a tape that we use for input and for storage. And we have a head pointing to some location on the tape, where we are on the tape currently. If we want to abstract a Turing machine, what's the issue? Or if we want to actually try to finitely compute a Turing machine in a finite amount of time, what's going to stop us from doing that? If you were trying to identify one of the components of the machine, it's the tape. The tape is why the configuration space of Turing machine is unbounded. If the tape were bounded, then the Turing machine itself would also be bounded. It would run out of room to run at some point, and we could just enumerate all the states it visits. So the way we approximate Turing machines and really any kind of interpreter whatsoever is to make the state space of that interpreter finite in some way. And so we can do that with a Turing machine very simply by cutting the tape. And in fact, we can cut it at any point, and what we do is wherever we place the cut, we just put some sort of bucket that approximates everything after that cut. So we can say, we don't know how many cells there are past this point, we don't know what's in those cells, but we know that it's a 0 or a 1. Granted, it doesn't tell you a lot, but it is a sound approximation of all the cells after that point. And we can go ahead and just approximate all the cells in the tape. I mean, why not? It's not like it's going to be that much more imprecise. And so this is an abstraction of a Turing machine. It's actually now it's just an NFA again. It's a non-deterministic finite automaton at this point. And we can just run it forward and see all the states that might be reachable. And if people actually cared about working with Turing machines, like if you were like the equivalent of a compiler optimizer for Turing machines, which I hope nobody is, then this very crude analysis right here could basically tell you which parts of the control state space of the Turing machine were actually reachable. And you could do dead code elimination on a Turing machine. So it would basically say you can't actually get to Q1, so you can throw it away if you want. But let's do it for something that looks a little more realistic. Let's do it for sort of a basic register transfer language. And if you look at the static analysis literature, there's actually a tremendous amount of research done on a language that looks exactly like this. And so it doesn't have procedures, and if you want to know how to handle things like procedures, these techniques again they scale up, and after the talk I can show you in a little more detail exactly how that's done. But the idea is basically the same. We're going to take an interpreter for this language and convert it into an abstract interpreter. I just want to point out at this point that basically everything I'm covering here, or about to cover, is available on a blog post that I've written called "What is Static Program Analysis?" So you don't have to take notes, and if you want to look ahead, you can look at this post right now. All the source code that I'm going to construct is available in this post. I'll give you a slightly different interpretation of that source code in this talk, though. So this is the language that we want to do static analysis over. You'll notice that this is more or less the language we just did an analysis of, this little expression language right here, except we've added variables. So our expressions can have variables inside of them now. And then we have some very simple statements. We have label, we have goto, we have variable assignment, and we have conditional branch. So that's, if your integers are unbounded, it's Turing complete, but in a really gruesome way. So what we'll do is turn it into S expressions that we can work with it easily. And the main idea here is to build a small step, purely functional interpreter for this language. That's the first thing we're going to do. And the way we do that is we come up with an injection that throws basically it takes your program and puts it into what we call a machine state. And we're going to come up with a function that takes us from one machine state to the next. And we can just apply this function over and over and over again to mimic program execution. So this is the particular style of interpreter that we want to build when we want to do abstract interpretation on top of it. You can do abstract interpretation on almost any kind of interpreter. But the methodology I'm going to show you today doesn't work as cleanly, meaning that the code that comes out the other end doesn't look as close to the original interpreter as what went in. So if you want to keep abstraction and static analysis simple, do it, construct your interpreter to work like this, and you'll be in good shape. All right. So what we need to do first is define this state space. What is an individual state of program execution? So we have to sort of ask, if we were to freeze the program as it was running, how do we encode the state of the program? And the answer in this case is a struct. It's going to have two fields. We'll have a sequence of statements. So basically it's going to have, think of this as the program counter. It's basically wherever we happen to be inside the program, plus wherever we're headed next, as well as a hash for the environment. So we're going to use a very simple EQ hash, which is a fast hash in Racket, that will map us from a variable to the integer to which it's currently bound. And then again, statements are just a list of statements. And on top of that, we want to build two helper functions. We want to build inject. So inject will take a program, which is a sequence of statements, and give us back a state. So that'd be pretty easy to write. And then we want to also construct step. So step will take a state and get us to the next state. So if we apply step over and over and over again, it's just going to march us forward. So let's go ahead and build these items. First, we'll go ahead and copy over our data type definition. So if you're curious, Racket actually does have, as of the past several years, a very powerful type system. So typed Racket allows you to basically add as much typing as you want. In addition to typed Racket, there's also a contract system inside of Racket. So contracts are basically like types that can only be evaluated at runtime, or at least they might have to be evaluated at runtime. So you can have a contract where you can say that this argument must be more than just an integer, it must be something like prime. So if you do like to do typed programming, you can still do it in Racket. And if you like more than typed programming, if you like contracted programming, you can do that in Racket as well. But I like to live dangerously, so I just put my types in comments. Okay, so we need a definition for states. So we'll build up a struct, and the state struct will have a list of statements and an environment, mapping variables to values. And we also need an injection function, which will take a program and give us back a state. So what should we create for the initial state given a sequence of statements? What seems reasonable? Yeah, empty hash, exactly. So we'll make a new state. What's that? Yeah, we'll just take the list of statements we just got, assuming we're going to start at the beginning of those, and we'll combine it with an empty hash. So there's a lot of syntaxes for defining empty hash in Racket. That one works just fine. So that'll take us from a program into the state space. Now we need that step function that can march us from state to state. So let's go ahead and define step. So it takes in a state, and it gives us back another state. So again, we're going to define step the same way we do everything in functional programming, which is we match on the input. And actually, let's take a step back. Let's do a match, but let's match on something a little bit different. Let's go ahead and match on the statements inside of the state, because we don't need to match on the environment. We're going to use the environment. We don't need to match on it for structural purposes. Although one of the nice things about pattern matching in Racket is that if you want to do a destructive pattern match on a hash, you can do it. You can match on hashes as well. I don't think any of it. Maybe Scala will let you do that too, but I can't think of others that allow that sort of behavior.
Probably not Scala pattern matching doesn't go into data structures or at least into types very well. So you can say I want to match on a set, but you can't specify what the type of data in the set are. So
well,
you can say a set, or you can pass in a class type.
Yeah.
If you use some special syntax, you can kind of make it work.
Sure.
It's not always possible to do.
Yeah. And certainly in Scala, you can define your own, define your own pattern matchers. Sort of. You can define unapply.
QHC recently got pattern synonyms, and it's had patterns for a while.
Yeah. Right. Yeah. Yeah. I've used view patterns in GT. It always seems a little bit clunky. It's. Oh, okay. I'll have to revisit that actually. Okay, so what I'm doing here is I'm just going to go ahead and pull out statements and environment, and then we're going to match on statements. And now what we need to do is just basically build a case for each kind of statement we could see. So let's see what those are. So one possibility is its label. Yeah, okay, we can do the empty list first. So if it's the empty list, then we're done. So this is actually interesting, so when we finish program execution, what should we return? Well, here we said we have to return another state. So what we'll return for now is false. Or actually, you know what? Let's just return the environment itself. Let's say that the environment is the answer of the program whenever we're done. And we can modify this up here to say that it's state plus environment. So there's a chance that we'll get just an environment back and we're done. And we might also see a label. But actually what this would really be is label as the head of a list. And there's the remainder of those statements. So if we see a label, is there anything we have to do to the environment to process a label? Are any variables going to change their value as a result of encountering a label in your code? No. It's basically just skip. We're just going to skip right over it. Yeah, we're just going to go to the next instruction by default. Oh, you're saying, like if we hit a go to, can we jump forward or backward?
Right.
No.
If you need to jump backward, you have to have an archive in some way of these
states. That's a good question. We're going to allow you to go backward. So what we'll add after this is a preprocessing step, which will build a hash map of the labels. So we'll match on label. And what this means, we're just going to build a new state, which is the rest paired with the same environment. And what's that? Oh, yeah. Oops. Thanks. So we could also see a goto. And if we see a goto, now we're going to assume that some map exists for giving us the statements and some label. Alright, so we'll have a statement map. And we'll start it off as a hash key as well. And we'll assume that's going to get updated. So if we have a goto, and we assume statement map is holding a map from labels to sequences of statements, what should the next state be here? So what should the statements be? Is that?
Well, find out what
Yeah.
label route.
Exactly. So we're going to look up in the statement map whatever that label happens to be. So we'll do hash ref statement map. I think it's hyphen that label right there. And the environment doesn't change. So same environment. So far so good. And then we could see assignment. So we could see an expression. So we have destination variable and an expression. And the rest, in this case, the next statement we're going to go to is the very next one, whatever rest happens to be. And in this case, the environment will change. So we're going to go ahead and do hash set. And we're going to set in the environment the destination variable to be what? So now it's an arithmetic expression that we want to evaluate. But we built something for that, right? Yeah, we built simple eval. So let's go ahead and call that. And it's almost good enough to work out of the box, except that we added something to expressions. So to make this more realistic, what did we add to expressions? Variables, exactly. So if we try to simple eval and we hit a variable, we have to look it up, which means that we have to add environment to simple eval. So we'll do that in just a second. And let's see, did we cover, oh, then we also have if. So I think we structured that as if expression go to label. So we have a condition right here, go to this label, otherwise fall through. So what we can do here is evaluate the condition. We use simple eval on the condition with the current environment, and we'll go ahead and branch on whether or not it's equal to 0. So if the condition is false, then we're going to return a new state that represents falling through. So we're going to go to the rest. Otherwise, we'll actually go ahead and look up that label on the hash map. And jump off to there with the same environment. All right, so we just built a very simple interpreter for this language. We need to extend simple eval very briefly. So let's do that. So simple eval has been updated. It takes an environment now, which means everywhere where we were doing a simple eval, we need an environment. It's going to be one additional case. Which is watching for a symbol. So if we see a variable and we have access to an environment, what should we do? Yeah, just look it up. So look it up in the hash map. Hash ref, environments, expression. Alright, so now I think it actually would work. In the interest of time, I will not drive a truck across this one. I think we'll just jump straight into abstracting this thing. So now that we have a concrete interpreter, what we want to do, actually, jump ahead. And we didn't build a preprocessor either, but it's, again, the code is online. So what we want to do is just make this interpreter operate over a finite state space. The way we're going to do that is, in this case, there's only one domain that's actually causing the state space to be infinite, and that happens to be integers. We've already figured out an abstraction for integers, so we're just going to reuse the same one. And what happens when you do this is you can inject a program into an initial state, and then when you run this interpreter, this abstract interpreter, instead of just going in a linear sequence of states now, what could happen is you could hit an if. Like if this is an if right here, and you don't have enough information to resolve whether it's 0 or non-zero anymore, you go in both directions. So abstract interpreters are inherently non-deterministic. And because there's only a finite amount of room to run, at some point, if you're doing anything like recursion or iteration, you're going to end up looping back to a state you've already seen. Something also that's not likely to happen if you're actually just running the program. And so, in some interpreters, you can get loops like this, but this happens all the time in abstract interpreters. So when you run an abstract interpreter on some input, what you get back is what we call an abstract state graph. And what this is it's a representation of all the possible paths of execution through your program. So whatever the program can actually do when it runs is encoded as some path through here. So again, we have to define the state space. We're just going to put hats on everything. That'll work just fine. For abstracting the components of the state space, we'll just say that instead of integers, we now have abstract integers. That works fine. Injection and stepping look essentially the same. It's actually that needs to change slightly because instead of getting back one state, we could get back multiple states. So we'll say you get back a list of states instead of just a single state when you step. And that accounts for the non-determinism. So there. Yeah, so by giving back a list, you can branch. And when you actually run these things in practice, this is actually what the abstract interpreters really look like. Or this is what these state graphs can look like. In fact, this is a relatively small program, as it turns out. This is like a 10-line program run at full precision in one of our static analyzers. So let's go ahead and just do the surgery on this thing. Let's make a copy of everything and abstract it. So just copy and paste. So, for very simple machines, yes. So this is actually sort of an open research topic right now. Is to what extent can we fully automate the process of an interpreter comes in, an abstract interpreter comes out? I mean, the goal here is to basically produce YAC, but for static analyzers. And again, for a machine like this, we're absolutely at the point where we know how to automate this kind of stuff. But you can make your semantics almost arbitrarily complex. And so we have a high-level methodology that humans can very easily apply right now, and we're sort of steadily ramping up the complexity. And what we've actually done is, since somebody mentioned, I think two people mentioned category theory and monads, something we're interested in, we've actually abstracted many of the properties of static analyses in general as monads. When there will come points during the abstraction process where it'll say, well, now you have to tell me how you want to abstract, say, integers, or how do you want to abstract memory addresses? And we've come up with ways of sort of generically specifying these things as monads. So you can say, well, I want you to use this abstraction for memory. And it's encapsulated entirely as a monad, and that will give you certain kinds of precision and behaviors when you actually run the analyzers. It's surprising that, monads just pop up all over the place in research, and we were surprised to find them there. But I can tell you a little bit more about why it's maybe not so surprising ultimately that they showed up in that place. All right. So for an abstract state is just a sequence of statements and an abstract environment. Our abstract injection function looks almost exactly the same. In fact, it is exactly the same. Nothing changed. We don't need to do it. We can use the same state map as before because we're just going to run a quick pre-processing step on the program, and then we have an abstract step function. This will give us back a list of abstract states and environments.
Is injecting a return abstract state?
Oh, right. Thanks. Good catch. It wasn't going to. Now it will. All right. So for the most part, we're just going to add hats to everything. This is great. So state. We're going to put a hat here. I could use a slightly better refactoring tool for this. So there's a hat on that. So if we run out the end of the program, we're going to return a list containing whatever that final environment was. If And for a lot of these, we have to wrap list around them, even though we're not actually returning more than one state. We still have to wrap them up in a list. I guess we don't in Racket. We could just check to see if one state comes back. So we'll go ahead and turn that into abstract. Yeah, so you can see why, at least for simple machines like this, you pretty much, we can automate it at this point. It's just a very deterministic process. And there's really, once we decided on how to abstract integers, everything's automatic at that point. So as far as automating this, basically the user has to decide, I want to abstract these values this way, and then it can take over from there. So that looks good. So if we go to some state, or if we go to a label, we're just going to return a single state where we jumped off to that sequence of statements. If we do assignment, then we're going to get one state back yet again. Oops. So get back a list of states. I hope I got all my parens balanced. Let's see. What's that? I'll find out. Yeah, I'll find out soon enough. And let's see. Did I miss anything here? So that has to be the environment is abstract. Simple eval is abstract. Oh, we didn't update simple eval to take environment, but let's pretend we did. And then when we get to if, again, we have a choice. So we can try to be smart. We can try to figure out if we can sort of precisely evaluate the conditional to know if we have only one way to go, or we just go both ways. So we can just wipe out the conditional entirely and say, just give me back both states anytime we ever hit an if. And two abstract states right here. Let's say unbound identifier. Oh, yeah. So I said this there. Oops. Okay, so it compiled. Let's assume it's correct. So, is this? Yeah, that one works for Haskell, I know. So what we would do at this point is just graph search. Basically say inject to some initial state, use this as your adjacency use step as your adjacency function, and just search until you basically explore the graph until you've seen everything. And once you stop seeing your states, you know you're done, and you've constructed a complete model of the execution of that program. And that is basically it. That is static analysis in a nutshell.
So you're exploring all the possible paths to the program with abstracted values. I guess if you're doing like dead code analysis, you have to kind of like compare that with this all possible statements and stages because I don't see them in the space that's been explored.
Right. So
the idea you're referring to.
Yeah, it's like if you dead code is actually a good example for what we just built. So you could do dead code elimination with a static analyzer like this. You'd certainly want to beef up the handling of if. You don't want to just go both ways all the time, because then you might actually encounter some dead code that's or the abstract interpreter might actually run over some dead code in that case. So if you want to do dead code elimination, beef up the handling of equality. So that it does try to return just 1 or 0 if possible. And then in your handling of if, check to see if you really do know if it's non-zero or not, and only go one way if possible.
You're really bounding the branches that are explored based on how you extract your values.
Right.
So if you type this, I don't know how you do it, but typing the value abstractions down to the pruning state.
Yes.
Search, right? Okay.
Yeah. So you get a tighter So here's an example of a tighter abstraction on integers. You can use an interval abstraction instead of just signs. So you can say, this integer, I don't know what it is, but I know it's between 0 and 3. And so there's you can do interval arithmetic in addition to signed arithmetic or something like that. Interval arithmetic is a little bit trickier because it's unbounded potentially. So you have to basically cut it off at some point and say, if your intervals just keep growing without bound, you have to step in and say, you've grown without bound for 10 iterations in a row. I'm gonna just put one into your bound up to infinity at this point, and that's called widening.
Really loosely bounded values, and that explores a lot.
Right.
Huge tree, or I really tight it down. It gets more to an action program.
Exactly. Exactly. Yeah. So yeah, like yeah.
This is like your diagram.
Yeah. So yeah, what you could do is you could take signs, and instead of having negative, 0, and positive, you could say negative, -1, 0, positive 1, and then positive. And then for some programs, if they only deal with -1, 0, and 1, you can then remain fully precise on those. Or and if programs use more than that, maybe you're fully precise on parts of the program and not on others, and you're going to get back a more precise modeling of all possible paths.
See more and more that
Exactly. Exactly. That's exactly what will happen.
I may have misheard you, but I thought you said at the beginning that this approach was well comparative languages, but not functional.
No, it's just a little bit trickier with functional. And actually, I came up with it for functional languages in the first place. Functional languages they're very difficult to analyze in general because of higher orderedness. When you have data flow and control flow recursively dependent upon one another. This actually it took us a long time to figure out how to solve that problem, and this is actually sort of the general technique underlying the solution to that problem. Because there were a lot of static analyses at the time that techniques like this were discovered, where they want to sort of pre-compute all the data flow in advance or pre-compute all the control flow in advance, and you just can't do that in a functional language where you have lambdas all over the place. So this actually. It does work very well for functional languages, and it works even better for imperative languages because they're so simple.
If you give this as a model of all static analyzers, this methodology is
So in fact, yeah, we spent a lot of time in my lab reimagining classic static analyses in this framework. So if you've seen data flow analyses and things like that, they can all be re-envisioned in what we call this small step framework. It can be done. So. When I finally get my sabbatical, I want to write a textbook on exactly that topic.
just recast the old.
Yeah, basically, right. Exactly. A unified approach to static analysis via small step interpretation. Yeah.
So your small step interpretation, that's basically small step operations.
Yes, it's exactly what it is. Yeah.
I'm sort of curious about what sorts of abstractions are helpful for the back-end stuff, or the security.
It's a great question. Yeah, so so like for if you're doing like avionics code, obviously signed analysis is nowhere near good enough for determining whether or not your airplane will crash. Yes. Right. So it's actually one of the major applications of this is detecting crashes in avionics control code, and there they have what they call polyhedral abstractions of integers, which are very high dimensional abstractions, which give you very high precision about exactly what not just an integer could be, but relationships between integers could be. So they and if your code doesn't use procedures or malloc, then those abstractions work very well. If you do a malloc, and then they die, and they die quickly. So there are some abstractions which are very fragile in the sense that if your code uses certain features, they break, but otherwise will give you incredibly precise results. Sign analysis is nice in that you can use whatever language features you want, and it's not going to blow up on you. So we do in my lab we have a large malware detection project through DARPA, and oddly enough we just use sign analysis for the basic values, because we're looking for is malicious behavior, and finding malicious behavior doesn't typically depend on doing a really good job with arithmetic. We could drop in more precise abstractions if we wanted to, but so far we really haven't found it all that necessary. In fact, much of the time, even a sign abstraction goes further than you need to. Sometimes just saying it's an integer is good enough. So yeah.
So I recently stumbled across this analysis in the GHC island. And they actually use sign analysis to map the problem onto sign sign analysis.
I didn't realize that. I do know that they are actually in the process of redoing their strictness analysis in this framework. One of my collaborators, who's now working on an office, Simon Peyton Jones, his name is Ilya Sergey, is rebuilding the strictness analysis inside of GHC using this approach. So it turns out the strictness analysis that was in GHC doesn't work so well.
I'm not sure, is any of that in GHC now?
It might actually be in there now because he was working on this with Simon like a year and a half ago. Then it might already be that then. Yeah, it could be. I think they actually published on this in Popular recently. I'd have to check. So it's if it's not in the mainline, it might be in one of the experimental branches at this point. Yeah.
What about when you're performing static analysis on like a statically typed language? Do you get better guarantees, more guarantees, or is it more complex?
So types sort of strictly help us. What happens a lot of time in static analysis is you get merging. And so by merging, I mean, if you're doing this on say, Java, you'll get to some point where it'll say, it's a cat or a dog. I'm not sure which one it is at this point. But if you pass through a type, and if that type is dog, you say, well, it definitely wasn't cat. So the types, if you trust that the type system is truly sound, then you can use that to filter as the analysis runs if you had some incidental merging. So for everything we do, we work in an untyped setting just because it makes it harder. And if we happen to be lucky enough to get types, then we're willing to use that information to improve the analysis. Absolutely. Although, one major application of this kind of work is type inference for untyped languages. So if you just get that state graph back, you can say, for this expression, tell me every state where this expression appeared and what kind of value is bound to it. And then you can bound its type that way.
Possibly also doing some interesting analysis if it's supposed to always be a real number, and occasionally it comes out with some exotic data.
Right, yeah, and you can check for nulls this way and things like that.
That's kind of what I was just going to ask. What are some of the things like that, like layers or whatever? But also, can you do this? What happens if you start looking at code that has disparate sources and sort of disparate types of languages as well? So like right now we've got all those data sets or whatever.
Right. So, if you have a code base that's written in multiple languages, right now the only solution is to compile down to some common intermediate format, and then do your analysis. There's no reason, in theory, we can't build sort of a multi-language semantics and then do an abstract interpretation of that. It's just that it's we just haven't done it. So, but there's nothing stopping us from doing it.
Could be really complicated when you're running an operating language.
Yeah, it exactly. Yeah. Actually, I'm going to say it's a little tricky. There is an effort to do multi-language semantics and try to figure out sort of if you're mixing typed and untyped code, who's at fault if something goes wrong. Yeah, the other guy, of course. Yep.
Oh, I just have a follow-up comment about when you mix different languages, you end up having to make your abstractions more general. So for example, if you're doing Java analysis, you don't have to have a full environment. When you're doing because it's not capturing stuff inside of other stuff, but it's using the frame pointer and make some simplifying assumptions about how these things interact. Whereas if you're also doing something with a scheme, you have to handle variable captions, which means you have to have full-fledged environments. And so you lose some of the additional precision you could have had in Java because you have to also do a scheme.
All right. There's that. And actually, I can think of one situation where we're actually considering doing multi-language semantics and multi-language analysis. And this is actually for our analysis of Android for malware. If you dip into native code, you don't want to just say, well, anything can happen now. we'd actually like to be able to just start analyzing the native code at that point in the same model of execution as the mainline interpreter. And also, if you go up a language, sometimes we go into JavaScript when you're analyzing Android applications. We'd like to be able to go up or down from delving bytecode essentially. And we finally got some money from DARPA to investigate the possibility of integrating a JavaScript analyzer and an Android analyzer at the same time, since so many of the Android applications we're analyzing are basically a web view with a bunch of HTML on the inside.
So is it helpful to the analysis task to transform high level
in general, yes. So we can operate directly on the original language, although it often makes the interpreter just way more complicated. So if you look at semantics that work on unnormalized raw languages, they're nightmarish. They're very complicated, and that complexity carries over to the abstract interpreter as well. So that's why so for the same reason that when you're working on a compiler, you transform down, you normalize, and things like that. You do the same thing before you do static analysis. And so what we will typically do is we'll normalize it first, maybe a few other things, but we won't do any of the transformations that start to lose information, like, say, closure conversion. So we won't go that far and then do static analysis. We would typically just normalize first. But for Dalvik, for instance, that we don't actually transform that at all when we do analysis of Android. We just operate directly in the Dalvik because it's more or less normalized Java code at that point.
Yep. They compile, right?
They do. Yes. Yeah. The language inside GHC is remarkably tiny. So I'm sure they're operating on that.
The operational semantics are defined on the STP language, which is like the core language with a little bit of extra annotation that helps the code generator. But the semantics itself is defined on the STP language.
Right. That's it. Halting problem solved.
Any other questions?